Hello, everyone, and thank you so much for attending this session. My name is Eliana Panagoulia, and I am a second-year PhD student at the Georgia Tech High Performance Building Lab under the supervision of Professor Tarek Raka. Today, I will be presenting work performed by myself and Dr. Raka in the first year of my PhD, focusing on performance analytics through building information modeling and retrofitting design. I will present a literature review about the current state of data integration and interoperability within retrofitting design practice. Our work is set on the premise that buildings do not exist only in their original as-built state, but rather in a perpetual cycle of design, construction, and retrofitting. Retrofitting, which is the focus of this research, offers significant benefits towards a sustainable future. It is critical, therefore, to bring the performance of our existing building stock up to standard. Existing buildings underperform due to degradation. If we invest in improving these buildings significantly, this is projected to create a net energy savings of 16% and 13 billion in cost savings in the next 10 years. Retrofitting requires knowing what to measure, what is there, and what its conditions are. Our environment embodies large, diverse amounts of data, and the tools at our disposal help us comprehend and improve our designs. Yet, currently, our tools do not, without great effort, provide this clarity. There are already established platforms that bring datasets together. Building information modeling, or BIM, which is becoming popular for retrofits, allows us to bring geometry together with data concerning other systems into a single environment. BIM has provided a good starting place, but the integration of performance in professional practice still relies heavily on manual document exchanges. The question is, how can we overcome this and offer more opportunities to expand the AEC industry's comprehension of the existing built environment? Our research is attempting to answer this by investigating how real-world data integration methods impact user comprehension of buildings. Especially in the case of performance analytics, users face three observed cases. The process of integrating performance feedback in the design creates a significant lag, as the processes of data preparation, sharing, and analyzing are time-consuming in the context of the current tools. Sometimes, to avoid this lag, design continues without incorporating performance feedback, which makes the feedback obsolete as the design has already moved on. Lastly, there is the case in which analysis is only included after the fact and does not impact the design. This occurs due to the federated nature of the AEC specializations and their specialized software, meaning the execution of any task requires a specialist and that the necessary data need a twofold transformation to be included in the design. In all cases, these challenges mean that performance analytics are not adequately incorporated into the design of a project. Data presents another challenge. There are data sets that are important for building retrofitting, but these have no place within the model. Even though these have a relationship to objects represented in the model, there is no way to link them to that geometry. The above problem occurs due to the rigid, predefined schema of software. This schema prefigures what can be represented in the first place within the software environment and what not. This lack of foreign data creates a reduction in content that fails to capture the diversity of the built environment, leading to a condition where relevant data are excluded and therefore obscured from the decision-making process. Since the tasks are federated, as noted earlier, we need a means to exchange data between environments. This is interoperability, which is a key concept in this paper. The ideal of interoperability is that data passes from platform A to platform B unaltered, while in reality, a portion of the data is either distorted or ends up missing entirely. This challenge occurs due to the fact that we have no common representation framework. Currently, we either have attempts at bringing multiple processes into a single UX, though the data for each remain internally federated, or attempts at generating singular monolithic schemas to represent all possible data, which is impossible. This lack of a common representation framework constrains the communication of data between specialists and software environments. So what if there was a better way? Data about the built environment requires agility to navigate and store effectively. What existing methods do is subtract away or flatten data as a part of the exchange process. We propose instead an approach based on the semantic web that sees data as an interconnected graph, as opposed to a predefined relational model. Retrofits, as an example, require a flexible representation in the beginning of the project to know exactly what is present and should therefore be represented. A semantic approach is an additive model in which each actor adds data to a whole representational model as opposed to trying to recreate that model for themselves. What is created is a shared view of the project where data are checked in and out and transformed only temporarily. This allows for multiple readings of a project to be created as dynamically as necessary. Currently, software allows for singular readings, which may or may not support specific workflows or analytical processes. The aim of this work is to take the multifarious datasets related to building retrofits and describe them within a semantic BIM model. The result of our review is the following proposed framework, which is composed of four main parts. The first part relates to the collection of data that should be incorporated. For example, RGB or IR images showing thermal anomalies and deterioration of building facades. The second step is data matching. This step identifies and maps various elements and their properties together into a 3D BIM data environment. Next is data processing and routing. This step turns this representation into a resource description framework or RDF triple store, allowing the data to be added to a semantic BIM model. Finally, the data integration and analysis step routes data out for further analysis and use by specialists. This framework does not reject the idea of federated task execution of current practices, but addresses the need for an effective data serializer to integrate and convert data to appropriate formats and communicate them in a meaningful way. Future work includes a survey to investigate in detail current user traits and workflows in energy retrofitting and BIM, a policy review of benchmarks for energy retrofitting, and the development of a vocabulary in the form of a semantic web ontology for representing buildings and their linked data. Thank you very much for your attention. I would like to inform you that we have a live survey that we invite you to participate in. You can find a shortened link for it on the screen. Also, if you have any questions or wish to know more about this work, please feel free to email myself or Dr. Raka at the addresses seen on screen.